Hi, I'm Edmund Owen, Principal Quantum Physicist at CC, and I'm looking forward to answering some questions about quantum technologies, so fire away. What I would love to be able to say in that answer is that it's not hard. Or no, not that it's not hard, that it's not mysterious. Quantum technologies are about controlling the microscopic world, and at that scale, quantum mechanics starts to become important. And there's nothing mysterious about quantum mechanics. It's just an area of science like any other. But how to exploit it, how to use it, how to make it do the things that we want, this is a new area that we're exploring, and that's what I'm really excited about quantum technologies. There are two answers to that question, I think. So one is that there's the trivial answer, which is that quantum systems are controlled by classical systems. So you'll have to have a computer which is controlling your quantum technology, reading out what's going on, and also understanding how to process that data. More fundamentally, there are problems which will definitely be good on quantum computers, but also problems which really aren't good for quantum computers. And being able to balance the workflow between classical computing and quantum computing is going to be really important, and understanding how those two systems interact together is a really exciting and interesting direction that research is pushing out today. So some technologies are going to find niche applications really early, and they're going to be things which can make a difference, maybe even today. There are other technologies which really aren't going to be mature or available for the market for commercial use for another 5, maybe 10, maybe 20 years. This is going to be an ongoing development of the technology. We often divide quantum technologies into 3 areas: quantum sensing, quantum communications, and quantum computing. So using quantum systems to sense the world around us can really enhance the sensitivity of our sensors, of our systems. We've done work on quantum magnetometry to understand how these systems can be used to measure things like brain activity. Your brain fires off electric signals, and there's a magnetic field that you can pick up with the sensor. Quantum computers offer a paradigm shift in what we can do with information processing. We've worked with classical computers for the last 50 years. We have them. They've changed the world in which we live. But there's new ways of processing information using quantum states which allow us to achieve and do new things. So there are some things which are a concern. So our cryptography, for example, is based on mathematically hard problems which are really difficult for classical computers to solve. Quantum computers can solve these easily. Quantum computing poses a threat to our information security, but quantum communications could offer a solution. Whilst we use mathematically difficult problems to encrypt and encode our data today, there are physical principles which can protect our information, which quantum communications could provide. This division into different technologies is something that's been useful up to today, but I think that moving into the future, we're really going to start blending these technologies. Some of the control systems that we use for sensing will become relevant for computing, communications, and other technologies. I see a world in which we stop talking about quantum sensing, communications, and computing, and just talk about quantum technologies as a whole. I think it's a really exciting time for quantum technologies. There are clear commercial use cases which are going to really make a difference to society and to businesses around the world. But I think there's also a lot of unknowns. We have new sensing technologies, new computational modalities. How do we use this? Where is it best going to be exploited and deployed? This is something which I'm really excited in pushing forward in CC.